this video, I'm going to show you a quick way to calculate the coefficient of friction. In the previous videos, we've discussed the force of friction and the coefficient of friction. In this case, let's say you have an object on an inclined surface with an angle of theta. So the force of gravity always points down. We'll always remember that it's always drawn downwards. The force of gravity is mass times acceleration of gravity, n times g. If this is theta, you know this is theta, so the force of gravity wants to push the box straight down, but the surface prevents the box from going straight down. So the surface redirects the force of gravity into two directions. It redirects it into a component that's pushing the box against the surface, and it redirects the force of gravity into a component that's pushing the box down the surface. This is the component that's responsible for pushing the box down the surface. This is the component of the force of gravity that's responsible for pushing the box into the surface. So mg cosine theta and mg sine theta. Because this is the component of the force of gravity that's pushing the box against the surface, then the surface pushes back with a normal force that is also equal to mg cosine theta. So let's say our first scenario is that the object stays at rest. If the object is on this inclined plane and it's not moving, it's staying at rest, that means that the force mg sine theta, which is trying to push the box straight down, is being countered by a force of static friction that is equal to it in opposite direction. So in this particular case, mg sine theta is the component that's trying to push the box down. And if the box does not move, then that means that the force of friction that is opposing the box motion must be just as strong as the force that's trying to push the box down the incline. So mg sine theta is equals to the force of friction. And then from there on, I try and solve for the coefficient of friction. So mg sine theta becomes equal to mu, which is the coefficient of friction. This is the letter mu. Mu times the normal force, that's the equation for the force of friction. And for the normal force, I plug in what the normal force stands for in this case, which is mg cosine theta. When you have this equation, mg sine theta equals mu mg cosine theta, you'll notice that the mg's, the mass and the gravitational acceleration, are going to cancel out from both sides of this equation. And you'll be left with sine theta is equals to mu cosine theta. Well, if you bring the cosine theta over to the left side, you have sine theta over cosine theta is equals to mu. Mu is the coefficient of friction. Sine theta over cosine theta can be simplified to tangent theta. So you can calculate the coefficient by setting it equals to tangent theta if you know the angle of incline, if you know the theta. What is this telling you? This is telling you that, look, if you put this object on the incline and you tilt the incline, you make it a steeper and steeper and steeper and steeper angle. You start off with 5 degrees steepness, then you go to 7 degrees steepness, then 10 degrees steepness, then 15, then 20, then 30. There's going to come a point when the box is no longer going to stay at rest and it's going to start moving. That point, at that point where it's just about to start moving, tells you what the coefficient of static friction is. Because at that point, the mg sine theta has overpowered the force of friction. So you can calculate the static coefficient of friction by increasing the incline slowly and steadily, and you reach a point when the box will no longer stay at rest and it's going to start moving. So you'll be able to calculate the static coefficient of friction. By the same logic, you can also calculate the kinetic coefficient of friction, because you can say, look, I'm going to find an inclined angle where the object is coming down, but it's coming down at a constant speed. If it's coming down at a constant speed, then that means that the force pushing it down is also equal to the force fighting against you. So if the object starts moving down at a constant speed, you can start off right here again. You can say the force pushing it down, mg sine theta, is equals to the force that's fighting me. But now you're not talking about static friction because the object is already sliding and sliding at a constant speed. So it's sliding, so now you're talking about kinetic friction. So you still can follow the same exact logical steps, and you can solve for the force of friction, and you'll realize you can find the coefficient of friction equal to tangent theta. But now, because the object was sliding, you're going to be solving not for the static friction, but you'll be solving for the kinetic friction. And the kinetic friction would be equals to tangent theta. So this is a very clear-cut way to calculate the coefficient of friction of a surface. You basically put an object on that surface and you start to raise the angle of theta. You start off with a lower angle to a steeper angle, and finally the point comes where the object doesn't stay at rest and starts moving. That is going to help you determine the static coefficient of friction. Then you realize that the object is, now you have to find an angle where the object is going to continue to move at a constant speed. Once you find that angle, and it's moving at a constant speed, you can still use the same idea, and you'll be able to find the kinetic coefficient of friction. Keep in mind that the kinetic coefficient of friction is less than the static coefficient of friction, because static friction is greater than kinetic friction. So that means that once you find that steep angle where the object started to move, then once it starts moving, you don't need as steep an angle to keep it moving at a constant speed. Then you'll probably lower the angle to keep it moving at a constant speed, because otherwise it's going to start accelerating down the incline.